Hello and welcome back. We are going to take a look at this next exercise here, where we are going to prove that n cubed is in the set of functions of big O n cubed plus 1. Okay, so let's just break down how we can use our properties to prove this statement here. And let's start by looking at the fact that this right here is annoying. It's annoying to have both those terms in the big O term. So let's take a look at our properties over here. And specifically, since I know my properties, I'm going to pull us down right here to 3.2. I'll pick that up and move it over here. Okay. Oh, no, not smaller. Get bigger. There we go. That's pretty big. Oh, God. Okay. So this here says that we can say that F is in big O of G if and only if G is in big omega of F. So this property tells us that we can actually proving that n cubed plus 1 is in big omega of n cubed is equivalent to proving n cubed in big O n cubed plus 1. And this statement right here is substantially simpler to prove than the previous one. Now, if we're not sure why this is actually true, again, you're allowed to just sort of take it at face value that this is a true property. But if you wanted to actually look at it, assume that this is some function f of n. And if we wanted to prove that it was in big O of g of n, that would be right up here. And if we wanted to prove that it was in big omega of g of n, that would be, actually, let me go one step further. This would be like saying this is function, I need another color. This is g of n, let's say. And so big O of g of n means it's some multiple, right, of g of n. So it's going to be like a little bit higher up. We can see where f of n is. And then we can say that this is omega of f of n. So what exactly is happening here is we are saying that if our function f of n is going to be inside of big O g of n, like this, that means that there's some multiple of g of n that will always keep us above f of n. That is equivalent to saying that our function g of n, meaning without all those multiples, so g of n, somewhere just below that upper bound, it has to be within big omega of f of n. So what that means is we're saying that as long as g of n falls between f of n as the best case, and well, this as the best case and this as the worst case, then we're able to say that for f of n, that's going to hold true as well. So sometimes drawing out this graph can help. Sometimes it makes it more confusing. Sometimes it's a lot easier to just take the property at face value and not try to understand it. But I'd like to try to give some context with the hope that it might help. Okay, so let's go ahead and we've pulled in this property that's allowing us to say by property 3.2, let's prove that n cubed plus 1 is going to be in big omega of n cubed. Then the next thing that we can do is we actually have to find a way to show that this is the case. So let's show how we know n cubed plus 1 is in big omega of n cubed. Let's start by looking at another property here. Let's look at a property 5.1. The property 5.1 is right here. Let's pick that up. We'll flop it back over here so that we can use it in our example. So this says for any constant c greater than 0, c times f is going to be in theta of f. So since 1 times n cubed is in theta of n cubed, because of course it is, we can then say that we know that n cubed on its own, right, obviously, is going to be in theta of n cubed. So what does this actually mean? This just means that n cubed grows at the rate of itself, right? N cubed grows at the rate of n cubed. So we know that that's pretty trivial. We understand that that's not really anything exciting, but a reminder that if something isn't theta, if we want to just go back and look at our properties one more time, let's find a theta property that I want to use here. Right here, I'll pull this one in actually. We know that, oh, I didn't have to click that, sorry. That since we know that n cubed is in omega, or sorry, theta of n cubed, we can look at 3.1 here and say by 3.1, n cubed must also be in big omega of n cubed, right? So the fact that it's in theta of n cubed means that we're allowed to say it's also in omega of n cubed. It's also in big O of n cubed, but we don't care about that for right now. We're just using this part of it, the fact that we know it's definitely going to be in big omega of n cubed. So this allows us to basically use these two properties. So this one was by 5.1, and then this one down here is by 3.1. So given this information, we can then look at another property to solve this proof. I don't know if that's really a solve is the right word there. Let's go ahead and look at a proof in the addition block here. Another one that specifically talks about that big omega. Let's go ahead and grab this one. Whoops. So if we grab this one right here, we can paste it down and we can, oh, that got really big, but that's fine. What we can say about this one here is that using 4.2, we know, so from above, we know that n cubed is in big omega of n cubed, right? That we already know. We can apply this same information now to show we can use this to show that n cubed plus 1 is in big omega of n cubed. Now, again, a reminder of what that means for the graph. We're talking about the big omega of n cubed being wherever on here, but n cubed plus 1 will just be somewhere above it, somewhere to the left of it, somewhere to the right of it. It won't make us fall below that line. So we know it's true just by looking at the graph. But in order to actually say it in words, we're going to use this property 4.2, which essentially says, by 4.2, it essentially says that f is in big omega of h. If f is in big omega of h, then adding a function such as g doesn't change the lower bound. That's what it's saying. It says if it's in big omega of h, then f plus anything else will stay in big omega of h. So then since n cubed is in big omega of n cubed, this implies n cubed plus 1 will be in big omega of n cubed. So we've now been able to show that n cubed plus 1 is in big omega of n cubed. So if we go back up to the top, 3.2, showing n cubed plus 1 is in big omega of n cubed is equivalent to showing n cubed is in big O of n cubed plus 1 as needed. And that's all there is to it. So since that plus 1 right here, right, since that plus 1 right here is that lower order term, like we did our drawing, we added that lower order term in, and we saw it doesn't change the lower bound. It would change potentially an upper bound. It could be a problem in the other direction, but it doesn't change the fact that we're in this lower bound of n cubed, right? Big omega is our lower bound. It's the best we can possibly do. If we want to add more to it, we're still going to be in, like, that doesn't move our lower bound. We're staying above our lower bound. So that's why we're able to use it. So even though n cubed plus 1 is technically a little bit larger than n cubed, since they still grow at the same rate as n approaches infinity, we know that n cubed is still a valid upper bound for n cubed plus 1, which allowed us to then bring this back around and use 3.2. Okay, I'm debating if I want to do another one in the same video. I think I'm gonna stop the video here, and let you, I think I'm gonna end up doing each of these individually, but that's okay. That way, if you want to take a pause, you can. If you want to try the next one on your own, you can. And if not, just join me in the next video where we will approach exercise 5. Okay, thanks everyone, and have a great rest of your day.